This video is on linear transformations. We're going to begin by looking at the linear parent function. A parent function is just sort of the simplest type of any kind of function. We're going to focus on just linear functions, lines, and the simplest version of that is the line y equals x. Notice my slope is 1 when there's no number in front of the x. We assume there's a 1 there. And the y-intercept is 0 because this is like saying plus 0. There's nothing after the x. So this is the graph of the line y equals x. And we can look at changes to the graph of a line by looking at what's called the parameters. The parameters are the parts of a linear function that define it, the thing that makes one line different from another line. And in terms of the function equation, the things that make them different are the m and the b. Those are the parameters, the slope and the y-intercept. And so we look at those to help us decide how the function is different, how one equation is different from another, and how one graph is different from the original or any other graph. In these cases below, let's look at what has changed. What has changed in comparison to the parent function? In this first graph, I'm looking at it and I'm going to look at the parameters, slope and y-intercept. And the slope appears to be the same, exactly the same sort of slant of the line. I could count rise over run and find out that they were the same, but I'm looking at it here. I can see it. But I do notice that the y-intercept has changed. In this case, the y-intercept is higher. It moved up, right? Here it looks like it's about 4. Here it was 0. And so that's called a shift up or a translation. Okay? And of course, it could have just as easily been moved down, and we would have said that it shifted down. And so changing the y-intercept has the effect of moving the line up or down. All right, what about this next one? What's different compared to the parent function? Again, we look at the parameters. What's slope and what's y-intercept? Well, the slope sort of looks similar. It's going in a different direction, isn't it? This is a positive slope of 1, and this, if I look at it, is a negative slope, and if I count it, I'd also find it's 1, but now negative 1. My y-intercept hasn't changed. It was 0 for the parent function, and it's still 0. And so it turns out that if we change the sign of slope, it has the effect of reflecting the line over the y-axis. Reflects over y-axis. So you can think of the y-axis as like a mirror. And so what's on this, a two-way mirror, I guess. What's on this side reflects and goes over here. And what's on this side reflects and comes over here. But you know how things look in the mirror. If you're standing 3 feet from the mirror, you still appear to be 3 feet from the mirror in your reflection as well. And so that's just what's happening. Distance is preserved, but in the opposite direction. Let's look at the next one. And I look at my slope, and this is definitely a less steep slope. It's flatter maybe, less steep. Flatter isn't really the mathematical way of looking at it, but I kind of look at it this way. What that's called when that happens is a shrink. A shrink. You can actually think of it as if this line was a piece of rubber band and you were holding it upright in front of you. If you shrink it, if you flatten it out, Doesn't it sort of expand sideways? And that's the way that you can think of this. Some people find it useful. But anything that's less steep or flatter would be considered a shrink. The last one we're looking at looks more steep. My y-intercept didn't change. It's still 0, just like in this blue one. But this one, it looks more steep. You might even look at it as taller or narrower. And it depends on the shape of the graph, how we see it. That word is narrower. But we call this, when it happens, a stretch. A stretch. So if you think about a rubber band upright in front of you, if you stretch it, top to bottom now, stretch it, it sort of gets skinnier and narrower. And that's just what's happening to my graph. If I took my line and grabbed it top to bottom and pulled my hands up and down, the line would become more steep. These are all transformations of the parent function. There's some notes that you need to take. We need to get these there. We're going to draw some pictures when you get to class. So you should pause the video. I'm going to make it full screen so you can see everything. Pause the video, copy these, but leave a line or two in between so that you have a chance to make a sketch next to it of what it is we're talking about. Okay, we're going to do a lot of practice with this in class, and in a few days we're going to do this with exponential functions as well, but this will get you used to the way an equation can be changed or transformed using a change in the parameters. For linear functions, that's m and b. So linear parent function is the line y equals x. It's a perfect diagonal on the graph. Transformations of linear functions always result in one or more of the following: a shift up or down, which happens by changing b, a stretch or a shrink, which happens by changing m, and a reflection over the y-axis, which is what happens when the slope changes its sign. Lastly, these can all be graphed. You have a graphing calculator, so use it. Look at what's happening. Don't try and guess just from the equation. Always graph the parent function in y1. That way, when you put the new function that you're trying to figure out in y2, you can compare it to the original right there on the same graph and see how it's different. All right, we'll get plenty more practice in class. Make sure if you didn't get the notes that you go back and pause the video appropriately to get those copied down.